How are you, all of you? I hope you are fine. Have you seen the previous e-learning content what I have developed? In the previous class, we have seen about charge, what does mean charge, properties of charge, and Coulomb's law. So try to see the previous lectures what I have uploaded in the e-learning content. In today's class, we will continue about a review of electromagnetic phenomena and variables, that is about electric field. We'll see these electric field lines and properties of electric field lines and what does mean voltage, current, energy, and power. So let's start from the first subtopic, that is about electric field. What is electric field? By definition, an electric field is a physical field that surrounds electrically charged particles. Charged particles. As we have already discussed in the previous class, charged objects may be attracted or repelled to each other depending on the sign of their charge. If they are opposites, they will attract to each other, and if they are similar charges, they may repel to each other. So when we say an electric field, it is a physical field that surrounds charged objects or charged particles. An electrically charged object sets up a force field around it. This force is known as electric field. Let's see an example. For the time being, if this in the first image, that is image A, there is no any net charge, but in the second uh, image, that is image B, there is a net charge. So what is the arrangement of these grass seeds? As you can see from this figure, the grass seeds is randomly arranged. But here in the figure B, they are arranged according to the electric field. In the figure A, there is no net electric charge and hence no electric field. The series point in a random direction. They are in a random direction. They are arranged in random direction due to there is no net charge. In the figure B, the seeds line up in the direction of electric field. Each seed experiences an electric force and the force goes to align with the field. As you can see here, they are aligned to the field since there is a net charge in this image. What is electric field lines? What is electric field lines? An electric field lines is an imaginary line or a curve drawn from a point of an electric field such that tangent to any point given the direction of the electric field at that point. Electric field lines are an excellent way of visualizing electric field. They were first introduced by Michael Faraday. These electric field lines are introduced by a scientist whose name is Michael Faraday. So this is the electric field lines, what it seems like. The electric field lines, what it seems like. What are the properties of these electric field lines? Let's see. The field lines never to intersect to each other. As you can see here, they will never intersect to each other. They will never to intersect to each other. The other thing is the field lines are perpendicular to the surface of the charge. They are perpendicular to the surface of the charge. Perpendicular to the surface of the charge. Each line is perpendicular to the surface of the charge. The magnitude of the charge and the number of field lines both are proportional to each other. The magnitude of the charge and the number of field lines both are proportional to each other. The start point of the field lines is the positive charge and the end point of is at the negative charge. As you can see here, the start point is a positive charge and the end point is a negative charge. The end point is the negative charge. This is some of the properties of the electric field lines. What is the electric field line at the point charge? At the point charge, you may have some test charge, that's the point charge. So what is the field line according to this test charge? The electric field of a point charge can be obtained from Coulomb's law. As you remember from previous class, Coulomb's law what states that the force between two electrostatic charges is directly proportional to the magnitude of the charges and inversely proportional to the square of the separation distance. So now we can relate the force with that of the Coulomb's law. So the force can be determined from that Coulomb's law. So the electric field E can be defined F divided by Q. because we have defined in the previous class the force is directly proportional to the square of inversely proportional to the square of the separation distance and directly proportional to the magnitude of the two charges. So here, as you can see here, the electric field is radially outward from the point charge in all directions. This is a point charge, this is a point charge. So it will radially outward to the point charge, from the point charge, radially outward from the point charge. The circles represent the spherical equipotential surface, as you can see here. This one is the equipotential surface. This one is the equipotential surface. From the Coulomb's law, you remember, and I have defined previously that the force is directly proportional to the magnitude of the charges and inversely proportional to the square of the separation distance. So the square of the separation distance, or the separation distance from this point to this point, is equal, and from this point to this point is equal. So these dots are the equipotential lines. The direction of the force that is exerted on a negative charge is opposite that which is exerted on a positive charge. The direction of the force that is exerted on a negative charge is opposite that which is exerted on a positive charge. This is we have already defined while we are discussing the previous class. Because an electric field has both magnitude and direction, the direction of the force on a positive charge is chosen arbitrarily as the direction of the electric field. The direction of the positive charge is chosen arbitrarily as the direction of the electric field. Therefore, the direction of an electric field is away from a positive charge and towards a negative charge, because similar charges will repel and opposite charges will attract. So as you can see from this figure, here it is the test charge and this is a positive charge. So if we place a positive test charge, it will push outward because they are similar charges. When we see this figure, we have a positive charge, so and negative charge is here, so it will attract. So the positive charge, the field, the direction of an electric field is away from a positive charge and towards a negative charge. Away from positive charge and towards a negative charge. What is the next topic is to say about voltage, current, energy, and power. So what is voltage? Voltage is defined as the electric potential difference per unit charge between 2 points in electric field. What does it mean electric field? We have defined. So between 2 points in electric field, there is a potential difference. This potential difference per unit charge is called voltage. In a static electric field, the work required to move per unit of charge between 2 points is known as voltage. Mathematically, we can express voltage means work done per charge, where work done is in joule and charge is in coulomb. We have seen in the previous class the unit of charge is coulomb. We can define the voltage as the amount of potential energy between 2 points in a circuit. We may have 2 points in an electric field, so that potential energy between 2 points is maybe defined as, or we can define as voltage. One point has a higher potential and the other point have a lower potential. The difference in charge between higher potential and lower potential is called voltage or potential difference. We call it voltage or potential difference. The voltage or the potential difference gives the force to electrons to flow through the circuit. Due to that potential difference, the electrons will flow. The higher the voltage, the greater the force, and hence the more electrons flowing through the circuit. Without voltage or potential difference, electrons will move randomly in free space. But if there is a voltage or a potential difference, it will flow in organized manner instead of in a random manner. What is current? What is current? Current is a stream of charged particles flowing through an electrical conductor or space. This is electric current. The moving charge particles are called charge carriers, which may be electrons, holes, and ions. In the conducting material, the electrons are the main charge carriers. In the semiconductor materials, it may be electrons or holes. In electrolytes, it may be ions. So, the stream of charged particles flowing through an electrical conductor or a space maybe is electric current. Is electric current. Current is the flow of rate of electric charge through a conducting medium with respect to time. The rate of electric charge, the rate of electric charge through a conducting medium with respect to time. We can represent the current by a capital I or a small I, a letter I, a letter I. What is the unit of a current? The unit of current is ampere. The unit of current is ampere. So mathematically, we can say current is dq by dt. dq by dt. This is current. This is current. What? When an electrical potential difference applied between 2 points in a conducting medium, an electric current starts flowing from higher potential to lower potential. But if 2 points in a circle are at the same potential, then the current can't flow because there is no any potential difference between that points. The magnitude of the current depends on the voltage or potential difference between 2 points. Hence, we can say that the current is the effect of voltage. Current is the effect of voltage. The other parameter is electrical energy. What is electrical energy? What is electrical energy? As per the definition of potential difference, we can say if one positive unit electrical charge, that is a body containing one coulomb, positive charge is traveled from point A to point B, it will do visual work. Visual work. Let's show you by using this. Let's say that this is the for the time being, let's say this is point A, and this is point B. So the potential difference between 2 points is V joule, V volt, the potential difference. So if one charge, if one coulomb charge is moved point A, from point A to point B, from point A to point B, the work done by this one coulomb charge will be V. The work done by this one coulomb charge will be V. But let's say the charges at point A is Q instead of one coulomb. So if we move a Q charge from point A to point B, a Q charge, so the work done will be QV, because the potential difference between point A and point B is V. So the work done to move a point charge from point A to point B will be work done, which is equal to QV. Let's say that the time taken to reach this Q charge from point A to point B is T. To point A to point B is T. So let's say the work done per time. That means rate dW by dt will be Q V, this one. So when we talk about this energy, we have assumed that this one is the work done to move from point A to point B, the work from point A to point B. So now instead of one coulomb charge, let's show you progressively by according to my note. If Q coulomb charges move from point A to point B, it will do VQ joule work, as I have showed you on the board. So if we move Q charge from this point to this point, it will do VQ joule work. VQ joule work. If the time taken by the Q column charge to travel from point A to point B is t seconds, then we can write the rate of work done as V Q by T. V Q by T, because the Q column charge is moved from point A to point B. The time taken to move from point A to point B is T. So this is the work done, the rate of work done. Again, we define the work done per second as power. In that case, the term VQT, that is this one, VQT would be electrical power. This will be electrical power. In the differential form, we can write electrical power P means V dQ by dt watt. Watt is the unit of power, so P power, which is equal to V times I. dQ by dt is the current, so it will be voltage times current. This is the power. But our target is to find the energy. The energy. So if this current flows through a conductor for a time t, we can say that the total work done by the charge E is V times I times T, joule. So we can say electrical energy is the work done by electric charge if current I ampere flows through a conductor or through any other conductive element. Potential difference V volts across it for time t second. The electrical energy will be VI times T. This is the electrical energy. This is the electrical energy. The electrical energy. What is the unit of electrical energy? What is the unit of electrical energy? Basically, we find the unit of electrical energy is joule. So when you say joule, it is 1 watt times 1 second. 1 watt times 1 second. Commercially, we also may use other units like watt hour, kilowatt hour, megawatt hour. These are the units of electric charge. The unit of electric charge. What is electrical power? We have already defined, but let's it in depth. Voltage and current are two basic parameters of an electric circuit, but only voltage and current are not sufficient to express the behavior of an electric circuit element. The behavior of an electric circuit. We may have different electric circuit elements, so the voltage and the current will not define the behavior of that electric circuit. We essentially need to know how much electric power a circuit element can handle. How much electric power? When you pay electric bill for electricity consumptions, we are actually paying the charge of electrical power for a specified period of time. The charges of electrical power for a specified period of time. You may, your appliances like different appliances like lamps or cooking stoves may work for a specified period of time, but how much power they consume for a specified period of time. This is what the electric utilities are asking for bill. So power is the rate of energy supplied or consumed by an electric element with respect to time. This is the power. Power is the rate of energy supplied or consumed by an electric element with respect to time. Suppose an element supplies or consumes an energy of dW joule for a time of dt second, for a time of dt second, then power of the element can be represented as P, which is equal to dW by dt. dW by dt. This is the power. This equation can also be rewritten as P dW by dt, which is equal to dW over dq times dq by dt. We are only adding this dq by dt, so it will be cancelled. That means multiplying both sides by 1 will not change the equation. So, but dW by dq is the voltage and dW by dt is the current. Since dW by dq is voltage and dW by dq by dt is the current I, so the power is voltage times current. Hence, as the expression of voltage and current in the equation are instantaneous, the power is also instantaneous. The expressed power is time varying. So the power of a circuit element is a product of voltage across the element and current through it. This is all about today's class. If you have any question, you can write on the comment box. Thank you very much for watching. We will see you in the next videos.